Okay, for the third and final video, we're going to pick up where we left off. Our next problem is we're going to calculate how much energy is transferred through a wall. So it says calculate the energy transfer in a wall section measuring 2 meters by 1 meter, and that's 0.04 meters thick with a thermal conductivity of 0.1. So they're telling us the how big the wall is, how thick the wall is, and how well it transfers energy through. Opposing sides of the wall have temperatures of 10 degrees and 5 degrees after 1 hour. So we're also given information about the temperature difference between inside and outside. Okay, so things that we know. We know the area that energy is being transferred through. It's 2 by 1 meter, so it's 2 meters squared. The thermal conductivity is 0.1. The thickness is 0.04 meters. The difference in temperature is 5 degrees. And the amount of time that it takes is 1 hour or 3,600 seconds. The things that we don't know is we don't know the rate of energy transfer, which is power. We don't know the amount of energy that's transferred. So these are the two other equations that we learned. So this is power is energy transfer divided by the time that it takes to transfer it. Power can also be calculated by K, which is our thermal conductivity, the area, the change in temperature, and the thickness of our material. So we can rearrange this equation to solve for Q, but we don't know P. But we can calculate P with this one. So the way that the PowerPoint shows it is they take this guy and they just slap it in the middle here. So they combine the equations. Or you could just do this as a two-step process. So you can solve for P and then plug P into this equation. Either way works. So they're going to show you the combined version. So K is 0.1. The area is 2. The change in temperature is 5. The thickness is 0.04, and the change in or the amount of time is 3,600 seconds, and that works out to be 90,000 joules. So we're going to do one like that in class. So the whole reason why we're doing this is to learn about what makes a good insulator and what doesn't. So we measure that by measuring something called the U value, which is how well something allows heat to pass through. So the U value can be calculated by taking the power and divided by the area and the time that it takes for that to happen. The opposite of the U value is the R value. It's the resistance, thermal resistance to energy flow. So if you know the U value, then you can just take 1 over U to give you the R value. And if we have multiple things, so in your house you've got drywall, you've got some insulation in there, there's some wall studs, and then you've got your exterior piece of wood, and then whatever siding you got. So all of those have an R value. All those resist the flow of energy. So we add each R value together to get the total R value for a wall. So here is an example of that. We've got drywall, we've got some fiberglass, we've got some kind of a foil to separate the two, and then there's empty space, which is filled with air, which also has an R value, and then we've got a layer of brick. So the R value for this section is going to be different than the R value for this section, but regardless, the R values are just added together. So for a normal section of the wall, it's going to be 27.7. For the area of the stud, it's going to be less because this stud is not as good as an insulator as the fiberglass part. So the fiberglass has an R value of 19, where the stud's got an R value of 6 or 7. So it's got a little bit less of an R value right here as opposed to right here. Okay, the last type of problem that we're going to talk about is radiant energy. When energy leaves our body, it radiates off us in the form of infrared energy. And we can calculate how much energy we lose using this equation. So radiation is the process by which energy is transmitted through a medium, including empty space, as electromagnetic waves. And most often for humans, losing heat is infrared radiation, but it could be other forms as well. So we're going to use something called Stefan's law, which is another scary looking formula, but it's really not that bad. So the amount of power that's lost, or the thermal energy, is so our radiant energy that's transferred is a constant. So it's 5.6696 times 10 to the negative 8th times the area over which the energy is transferred times another constant. So whatever the thing is that we're measuring will have a predetermined constant, so we just have to look that value up. So far there's two constant numbers and then one that we have to calculate, and then the temperature. So the starting temperature and the ending temperature, or whatever. And the tricky part is this is to the 4th power. So you're going to want, and mathematically you're going to measure this to the 4th, or calculate that to the 4th, calculate this one to the 4th, then subtract them, and then you can do the rest of your multiplication. So here's an example. So a student is watching the weather, deciding what clothes to wear. Their bedroom is 65 degrees and their skin temperature is 91 degrees. So determine the amount of energy transferred from the student's body in the 15 minutes they spend watching the weather. So we need to know what the how well or how poorly the skin gives off energy. So it has an emissivity of 0.9, and the surface area of the body is about 1.3 meters. So we know the area, we know the emissivity. Stefan's constant is always the same. We know the temperature of the room, we know the temperature of the skin, and the amount of time that they stood in front of the TV watching the weather. So we should have everything we need to solve this problem. So we need to solve for one of our temperatures. Or I'm sorry, we're going to solve for P, but we need to do the temperature part first. Sorry, I misspoke there. So we've got 91 degrees is the first body temperature, and then the room temperature is 65 degrees, so that's going to be our second temperature. We're going to multiply each of those to the 4th power, and then subtract them from each other. So we take this one minus this one, and so that gives us in degrees Kelvin this big number. So you can represent it like this, or you can represent it like this. Either way is fine by me. So now that we know the temperature difference, we can go back and fill everything else in. So we know the constant, we know the area, and we know the emissivity for the human body. And so we plug everything in, and this is the number of watts that we have. So now that we know the number of watts, we also know the amount of time that it took, and so we can calculate Q now by multiplying by the number of seconds that took to happen and get our joules. And then so the last part of the PowerPoint is talking about ways that we would apply all this. So solar panels are a big one, and energy from the earth, but that's going to wrap up. You can read those on your own, so that's going to wrap up this video.